Hello, this presentation is all about electrical power. The syllabus statements that we're going to be covering for Edexcel are that you should be able to use the relationship between power, current and voltage and then be able to select the correct fuse. You should also then be able to calculate the total energy transferred, so be sure to come back to the syllabus statements at the end of this presentation and check how well you have met them. So let's remind ourselves exactly what we mean by power. Well, power tells us how quickly energy is being transferred from one form to another. And so here is the equation: power is the energy transferred over the time. Now if we remember that the units of energy is the joule and the unit of time is the second, then we can see that power must have the units of joules per second. And 1 joule per second is called a watt. So remember, 1 watt is 1 joule per second. So this is a very easy way of working out the total power if you know the total energy that's being transferred and you know the time taken. Remember though that not all the energy transfers will be useful. Some of the energy may be lost. So what does this mean in real terms? If we have a power rating of 10 watts, it means that 10 joules are transferred to other forms of energy each and every second. Now let's look at a real-life application. These two bulbs give out the same light. One is rated at 60 watts and the other is rated at an equivalent of 14 watts. Now remembering that 1 watt is 1 joule per second, which bulb uses the most electrical energy? Well, clearly this bulb here is the one that's rated at 60 watts, and this means that it transfers 60 joules of energy each and every second. Some of that energy is transferred into light, but quite a lot of it is transferred into heat and lost, so it's not useful energy. The bulb at the top is an energy efficient bulb, and that only transfers 14 joules per second. If you look around your house, you'll see that the power rating is given on many appliances. Here are some that I found in my house. Here you can see this appliance operates at 20 watts. So that means 20 joules are transferred into other forms, 20 joules of electrical energy are transferred into other forms of energy per second. Here is my kettle. That transfers 2000 joules of energy in each second. So thankfully I don't leave my kettle on all day. Here is the fan in my bedroom. This transfers 50 watts, so that means 50 joules of energy each second. Why not have a look around your house and see how many stickers like this you can find? Now there are lots of times where we want to be able to calculate the electrical power, and as you can remember from before, we need to know the total energy transferred in joules and the time that the appliance has been running for. This isn't always easy to measure, but what we can measure in the laboratory is the current and also the voltage. And so we can use the following equation to calculate the electrical power of a device. So power then, the equation tells us that power is equal to the current times the voltage, and of course the units of power is the watt, where 1 watt is 1 joule per second. I is the symbol for current, which is measured in amps, and V is the symbol for potential difference, which is measured in volts. Here is a question for you to try and put some of what you've learned into practice. Remember for each of these questions to pause the presentation and try the question before putting it back on to check the answer. Okay, so the first thing we need to do is write down our equation either in symbols or words, and you can see here that we have volts and we have a current, so we can use P is I times V. I'm going to miss out the times symbol. So here we have a current of 20 amps times 230 volts, and so the power is 4,600 joules per second, or 4,600 watts. Here is another straightforward question for you to try, but look at the question carefully and see what information you have before choosing the equation that you're going to use. In this case, I have the total energy and I've got the time taken, and so the question enables me to select this equation to calculate the power, but I have the energy, which is 10,000 joules, and the time taken, which is 25 seconds. And so the total power is 400 watts, or 400 joules per second. This question requires a rearrangement, so look carefully at the information you have, decide which equation is appropriate, and then rearrange it to solve for the potential difference. Remember, if you're not very confident at rearranging equations, then you can always write the equation down. So here I could write power is current times voltage, because I have power and current, but I don't have voltage. And then if I wanted, I could write 2 is equal to 0.8 times, and then the thing that I'm looking for, which is the voltage. And then a lot of people then can see that they need to divide the 2 by the 0.8. If you want to rearrange it in symbol form, then P is I times V. Remembering, if we want to get V by itself, we need to undo this multiplication. So this simply becomes V is power divided by the current, which is 2 watts divided by 0.8 amps, which of course gives us 2.5 volts. And remember that you can always check this by substituting back into the original equation. So here is another equation. Once again, look carefully at the information you have and decide what it is that you're solving for. Then come back and check the answer. In this question, we're trying to find the current I, and we already have the potential difference, 12, and the power of 3 watts. And so we could use the equation P is I times V, and then either substitute in the numbers directly. So for example, this would be 3 watts is the current times 12, or we could rearrange it to give the current is the power divided by the voltage, because the current is multiplied by the voltage, so in order to get the current by itself we need to divide both sides by V. And so in that case, if we slot in the numbers, we get 3 divided by 12, and so the current is 0.25 amps. Don't forget that unit. This next section then is about choosing the right fuse. Quite often, after you've worked out the current, the next thing you need to do is to select the correct fuse. The most common fuses are 3 amp, 5 amp and 13 amp. And the trick is always select the one that's the next one above the operating current of the device that you've worked out the current for. So for example, if you have a table lamp that uses a current of 0.5 amps, then you would need a 3 amp fuse, because that's the next one above 0.05 amps. A 9 amp toaster would need a 13 amp fuse, because that's the next fuse above 9 amps. Here is a question for you to practice that skill. So we've got a kettle that runs from the mains and is rated at 1.5 kilowatts. The first thing you need to do is calculate what is the current that it uses, and then next you need to select the correct fuse for this device. So please pause and then come back and check your answers. Well, let's deal with the first part. This type of question can sometimes confuse people because it doesn't give the voltage, but remembering mains voltage, use 230 volts. And here also we've got another banana skin, in that the kettle is rated at 1.5 kilowatts, remembering that kilo anything is 1000. So that means 1000 watts. So if kilo is 1000, the kettle is rated at 1500 watts. So now we've converted what we have in the question into something that we can use. We can calculate the current. So we've got voltage and power. So using P equals I times V, we can either write the numbers in or we can rearrange it and solve for the current. So I has been multiplied by the voltage, and so to get rid of the voltage on this side, the V, I need to divide both sides by V. So that gives me that the current is the power divided by the potential difference or voltage. So the power I know is 1500 watts. The volt is the main voltage supply, which is 230 volts, which gives me a current of, and I round it as 6.5 amps. So what size fuse then from these would you select? Well, the correct choice in this case would be 13 amps, because then that's the next size up. So the size fuse that would be the correct choice would be 13 amps. Here are a couple of questions for you to think about. What would happen if you used a 3 amp fuse with an appliance that draws a current of 5 amps? What would happen if you used a 13 amp fuse in an appliance that needs a 2 amp current to operate? So have a think about these for a couple of minutes and then put the recording back on. Well, for the first case, if you had a 3 amp fuse, the appliance wouldn't work because it needs a current of 5 amps. So that means that a 3 amp fuse would melt before you had enough current in order for the appliance to work. In the second case, if you use a fuse that's way too high, then that means that the current could go dangerously high, much above the operating current actually needed, and cause overheating long before the fuse melted. So that's why it's really important for safety reasons to make sure that you don't use a fuse that's too high, and obviously if you want your device to work, you don't want to use a fuse that is rated too low. Now here is the challenge for you. We want to be able to calculate the energy transferred. So if I tell you that a device has a power rating of 10 watts, how much energy does it transfer in 1 second? Remember that 1 watt is 1 joule per second. Have a think. Well, 10 watts is 10 joules per second, so in each second the total energy transferred is 10 joules. So how much energy then will be transferred in 2 seconds? How much energy in 20 seconds? Have a think about that for a moment. Well, if 10 watts is 10 joules per second, then in 2 seconds we're going to transfer 10 joules per second times 2 seconds, which is of course going to be 20 joules. In 20 seconds, that means I'm going to be transferring 10 joules per second each second. So if I multiply that by the total time of 20 seconds, I know that I will have transferred 200 joules. So you can see that if you know how many joules per second are being used, and you know how many seconds the device is running for, then it's easy to calculate the total energy transferred. And if you manage to do that, then you've already worked out what the next equations are. So in order to calculate the energy transferred then, we just need to take the power and multiply it by the time. We have to make sure that the time is in SI units of seconds though, so if you have something that's in minutes, be sure to convert it to seconds first. So here we have the equation both in word and symbol form, where E is the energy measured in joules, P is the power measured in watts, where 1 watt is 1 joule per second, and T is the time in seconds. Now, here's another challenge for you. Let's say that you want to calculate the total energy transferred, but you don't actually know what the power is. Perhaps you just have the current and the potential difference or voltage. How would you calculate this power? Well, remember, if we've got current and voltage, we can use P is equal to I times V. So you'd need to use that first and then multiply by the time. If you prefer, we can go one step forward and write an expression for the energy in terms of I and V rather than P. So we can just replace the power by I times V. And then, of course, to calculate the energy, we need to multiply that by T. So this gives us our next equation. So we're combining our equation for power when we have current and voltage, and we combine that with the equation for energy, which is power times time, and so you can come up with the very useful expression that energy is current times voltage times time. Now, it doesn't matter which way you put these in. Lots of people like to remember it as ITV or even VIT. It really doesn't matter what order you perform the calculations in. Here are a couple of questions to check your understanding. So the first one is about a 1200 microwave oven that runs for 50 seconds. It's always good practice to identify what information you have before you start. Try this question now and then check your answer. Well, this is a fairly straightforward question. I've got the power of 1200 watts and I know the time, and thankfully it's already in seconds, so I don't need to convert it. So how much energy does it use? So it uses 1200 joules per second for 50 seconds, so I can use this equation. Energy is the power times the time, because I already have the power in watts. So that's 1200 watts times 50 seconds, which is of course equal to 60,000 joules. Or you could write that as 60 kilojoules. It doesn't really matter. Look very carefully at this question. What information do you have? What equation do you think is appropriate? And do you need to change any of the units? Well, looking at the question, I can see that I've got V, and I've got I, and I've got a time, but that's 30 minutes, so I need to transfer that to seconds. So in order to transfer 30 minutes to seconds, I need to multiply it by 60. So 30 times 60 seconds gives me a total of 1800 seconds. So that's that bit dealt with. Now let's see what else we've got. Well, as I said before, we've got I and V and T now, and so we can use the equation that the total energy transferred is the current, which is 1, times the potential difference, which is 5 volts, times 1800 seconds. Which of course means that we transfer a total amount of 9,000 joules in that 30 minutes. So here is a super quick summary slide. Power is how much energy is transferred per second, and we can find it using the equation power is energy divided by time, where time must be in seconds. Power is measured in watts, where 1 watt is 1 joule per second. And we can find electrical power if we know the current and the voltage, using power is current times voltage. We can calculate the current using power is current times voltage, this equation here, to calculate the current needed for a device to run, and then select the correct fuse, which should always be the next one above the current that's needed. We can also work out the total energy transferred if we know the power and the time. If we don't know the power but we have the current and voltage, then we can combine these two equations, this one and this one here, to give us this final very useful equation that the total energy transferred is the current times the voltage times the time. Now is the time to go back and check against the syllabus statements that you're happy with what you have covered so far, and then go on and practice some of these self-assessment questions that you will find posted for you.